Hi, everyone, and good morning to those on the West Coast. Today, we'll be presenting about the Texas Advanced Computing Center, or TACC for short.
So Natalie isn't here, but she's a fifth year at Arizona State University studying information technology. My name is Roger Ali. I'm a freshman studying computer science with a minor in mathematics at the Purdue School of Science at Indiana University, Purdue University here in Indianapolis.
I'm Elle Fahey. I'm a sophomore studying applied computational math and statistics at the University of Notre Dame.
I'm Saad, and I'm a freshman at UAB studying computer science and mathematics.
So what is TACC? The Texas Advanced Computing Center at the University of Texas in Austin is a premier research facility offering cutting-edge computational resources and support to researchers nationwide, allowing them to make groundbreaking discoveries. TACC's environment is home to numerous advanced computing technologies, including systems such as Frontera, Stampede, Stallion, Corral, and more, all with varying uses aimed towards making scientific progress. Over the past 2 decades, the National Science Foundation has generously funded numerous projects at TACC. In the fiscal year 2020 alone, the University of Texas at Austin secured the top spot among universities for NSF-funded research, amassing $144 million, with a substantial share allocated to TACC projects and resource development.
Examining TACC's research, we aim to explore its contribution to scientific progress across various disciplines. And through this, we found out that TACC's projects span from biological sciences to astrophysics. And through the NSF's Extreme Science and Engineering Discovery Environment, short for XSEDE initiative, TACC's resources are accessible to the national academic research community, fostering collaboration advancements and discoveries. For this presentation, we have selected 4 exemplary research projects utilizing TACC resources to showcase TACC's resources, starting with climate modeling and weather prediction. The CESM project with NCAR leveraged TACC's Frontera supercomputer for high-resolution simulations of global climate patterns, revealing the effects of rising greenhouse gas emissions. The diagram shows that the high-resolution CESM model works well on Frontera and can use up to 800 nodes, which is about 45,000 cores efficiently. However, one part of the CESM model, called POP2, which is Parallel Ocean Program, responsible for simulating ocean circulation, doesn't work efficiently beyond 800 nodes. When CESM needs to save data frequently, its performance drops by about 40%. But despite all of this, the 6 years per day performance of the high-resolution CESM on Frontera is among the best of this type of climate model on any supercomputer. TACC also leverages high-performance computing to streamline drug discovery, quickly screening numerous compounds to identify promising candidates for diseases like cancer and Alzheimer's. The drug discovery at TACC program utilizes virtual screenings and molecular simulations, expediting drug development and bringing us closer to effective therapies for these severe conditions. TACC is utilizing HPC and AI-driven molecular dynamic simulations to expedite drug discovery in the fight against COVID-19, which rapidly screens potential molecules and supports innovative research. In the field of astrophysics and cosmology, the Illustris project used the TACC supercomputers to generate a model of the universe's evolution, simulating at least 13 billion years of cosmic evolution, which is huge. And it also provides an accurate representation of certain observed features of the universe. This large-scale simulation here spans the cube-shaped piece of the universe that is 350 million light years long on each side and required running across multiple computing centers over a span of months due to the vast amount of data involved. TACC supercomputers, including Frontera, were also utilized by SCEC, which ran computationally intensive simulations of hundreds of thousands of years of seismic history in California, helping to determine the likelihood and impact of earthquakes over an entire region and providing valuable data for developing more resilient building designs. Frontera is one of... You can go ahead, Ellie. Sorry.
Frontera, created in 2018, is an NSF-funded petascale computing system and is one of the most powerful supercomputers in the world. Frontera is used across the United States by researchers and scientists alike for work ranging from the cosmic to the quantum scale. Frontera serves as a leadership class system in NSF's cyber infrastructure ecosystem. Through the NSF petascale computing resource allocations program, more than 55 million node hours each year have been made available for use for researchers. Now we'll discuss the data lifecycle of TACC, where one of the pre-mentioned supercomputers plays a significant role. TACC manages a diverse data types for various research projects, including simulation, experimental, and observational data. Simulation data involves molecular dynamics and climate simulations, while experimental data includes genomics and high-energy physics. Observational data, collected from real-world situations in domains like astronomy and geophysics, is stored in TACC systems such as Corral and Ranch, facilitating data sharing and collaboration. Examples of observational data include sensor information, satellite imagery, and natural hazard research.
So researchers using TACC resources often create various data products derived from their raw data. And these data products can be intermediate results, process data, or final results. And this depends on the specific research project. These data products can be used in different ways. So first, the products can be used to perform further analysis, develop models, or make predictions. An example of this is the AdCirc model. AdCirc is a system of computer programs for solving time-dependent free surface calculation and transport problem in 2 and 3 dimensions. These calculations lead to the accurate prediction of storm surge and flooding. The raw data processed through AdCirc model generates high-resolution storm surge predictions and flood inundation maps, which can be used by emergency management agencies, urban planners, and infrastructure designers to better understand the potential impacts of hurricanes and develop more resilient coastal communities. Additionally, through these statistical analyses, the researchers were able to confirm the detection of gravitational waves and study their properties, which led to a better understanding of astrophysical phenomena such as the merging of black holes and neutron stars. And to visualize their calculations, they created hundreds of maps which showed information about storm surges, floods, winds, and wave information, which was valuable for emergency services, insurance companies, and researchers. So next I'll talk about data capture. Data capture involves collecting the raw data from different sources such as sensors, monitoring stations, experiments, simulations, and remote sensing technologies. TACC supports data capture in 3 main ways. So first is through high performance computing systems like Frontiera, Stampede 2, and Lone Star 5. And these can handle large scale data and complex calculations for experiments. The second way is through data storage systems like Ranch, Coral, and Stockyard. And these help with efficient ingestion, storage, organization, and management of raw data. So for example, Ranch helps with data archival. The system prioritizes data durability and integrity and uses error detection and correction mechanisms to ensure that the data remains intact and accessible over time. It provides hierarchical storage management, and it automatically migrates infrequently accessed data to tape storage. And this can help with reducing the cost of operation. And the third way that TACC supports data capture is through data sharing and research platforms like DesignSafe. And these promote data capture management, sharing, and collaboration for natural hazard research through services such as TACC's data collection catalog.
You're mute, Ellie.
Ooh, sorry. Now we'll talk about how data is processed, which is the next step in the data lifecycle at TACC. First and foremost, TACC offers services for visualization software packages that researchers can use to develop visuals of their data. These include Visit and ParaView, which are highly efficient and user-friendly. In addition, TACC utilizes MPI and OpenMP, which are popular parallel programming models that enable the efficient processing of large data sets in high-performance computing environments. This all helps researchers to process their data in a much more quick and efficient manner. TACC's JetStream platform is another great resource for researchers. The platform provides pre-configured virtual machines with pre-installed software stacks, allowing researchers to more efficiently access specialized environments for data processing, analysis, modeling, visualization, and more, without the need for manual installation and configuration. Finally, Globus and Data Transfer Node are essential tools for data capture processing. Globus simplifies the process of transferring large data sets between different storage systems, while DTN provides high-speed data transfer capabilities, ensuring that the researchers have the ability to transfer their data quickly and efficiently. Next, for data storage, iRods also helps with data dissemination, which is making data accessible for the broader scientific community. iRods allows researchers to configure, define, implement, and enforce data management policies for their projects. By automating data management tasks like data organization, metadata management, and data sharing, iRods helps researchers disseminate their data more efficiently in a standardized manner while saving them time and effort. TACC's web-based data portals, like the TACC Storage Gateway, provides researchers with an accessible platform to share their data, tools, and workflows with collaborators to the public. By using these portals, researchers can reach a wider audience, engage with their peers, and contribute to the advancement of scientific knowledge.
We'll discuss TACC's best practices for data management and how they can be applied to other research domains. For data storage, standardized format conventions and choosing the right storage solution based on the data needs is what TACC does. TACC offers various storage systems, as discussed earlier, like Granch, Coral, and Stockyard. And they also employ version control systems for tracking changes and collaboration. Regarding data sharing, they use platforms like TACC Science Gateway or iRods to facilitate collaboration and discovery on a greater scale. They also implement proper access controls such as ACLs to ensure data security. Finally, they also ensure transparent and reproducible research by documenting data, collecting data, and processing and using proper analysis method properly. They also create comprehensive metadata and employ standardized data formats such as any NetCDF, which can be shown here in the diagram, for better data management. I'll also discuss about the security aspect that TACC employs. Since TACC works with highly sensitive data, it's crucial to see what strategies are being used to ensure the security and privacy of these data sets. TACC has implemented stringent security measures to support researchers working with highly sensitive data, like medical records or financial data. TACC employs MFA, which is multi-factor authentication, using their in-house developed open MFA system, which adds an extra layer of protection against brute force attacks. In the previous diagram, this is what open MFA is in simple words, which employs security on a larger scale. And they have also used additional security such as ACLs to manage permissions within their file systems, ensuring that only authorized users can access these sensitive data sets. By adopting these security strategies and technologies, TACC ensures the security and privacy of sensitive data while also accommodating the diverse access needs of its researchers. That is all the information we have today about TACC, and we hope that you all learned something interesting about the facility. The QR codes right here take you to the website and the Kahoot, which can be a good way to re-emphasize all the facts that you may have learned about TACC. If anyone has any questions, we are more than happy to answer them. And thank you so much for taking the time to listen to us about TACC.
Thank you.
Good. So the major facility that was assigned to us is MagLab. We are group 2. My name is Rashi. I'm a senior at IUPUI, majoring in computer science with a minor in mathematics.
I'm Eddie. I'm a sophomore at Notre Dame, majoring in computer science and applied computational math and stats.
And I'm Gareth. I'm a freshman at LSU, and I'm actually a major in mechanical engineering.
And as you can see, we have various people coming from various different disciplines, and all of us took a lot of interest in this project. So let's start with the presentation. Okay, the first question that arises after looking at the title is, what is MagLab? So MagLab is a large scientific research facility that specializes in studying the properties and behavior of materials under extreme conditions. It is short for the National High Magnetic Field Laboratory. The science mission for the MagLab is to advance the understanding of the fundamental properties and behavior of materials under extreme conditions, particularly in high magnetic field. MagLab's research aimed to provide insight into the fundamental laws of physics, chemistry, and biology that govern the behavior of matter, and to develop new materials with novel properties for a wide range of applications. Now let's discuss how is MagLab trying to accomplish this goal. The first is developing new materials with novel approaches. One of the primary goals of MagLab's research is to develop new materials with unique properties that can be used in a wide range of applications. For example, researchers at MagLab are studying the properties of superconductors, which can conduct electricity with zero resistance and can be used to revolutionize the power transmission and storage. Second is understanding the fundamental laws of physics, chemistry, and biology. MagLab's research aims to deepen our understanding of underlying laws that govern the behavior of matter. For example, the researchers at MagLab are studying the behavior of materials under extreme conditions such as high magnetic fields or low temperatures to better understand how the laws of physics chemistry apply in these situations. Third is improving medical treatments. So for this, the researchers at MagLab are studying the properties of biomolecules such as proteins and nucleic acid to understand how they functions and to develop new drugs and therapies. Fourth is advancing technology. MagLab's research aims to provide advancing technology, particularly in the field of energy storage, electronics, and computing. Now let's understand how they try to achieve this mission. There are multiple ways in which MagLab is approaching its mission. However, we will be discussing these three. First is the interdisciplinary collaboration. MagLab brings together researchers from a wide range of scientific disciplines, including physics, chemistry, material science, and biochemistry. By working across traditional discipline and disciplinary boundaries, MagLab researchers are able to tackle complex scientific problems and develop new insight and innovations. Second is outreach and education program. MagLab is committed to promoting scientific literacy and engaging with the public. The lab offers a range of outreach and educational programs, including tours, lectures, and hand-on activities to help educate and inspire the next generation of scientists. Third is partnership with industries and government. MagLab works closely with industry and government partners to transfer its scientific discoveries and innovations into practical applications. For example, MagLab collaborates with companies in the energy and technology sector to develop new material and technologies that can be used in commercial applications.
Okay, so MagLab is organized into, I think, 7 different facilities, which are located across the United States. But they collaborate mainly with Florida State University in Tallahassee. So that's where most of their facilities are located. And each facility, although they all utilize magnets, but they utilize magnets in different ways. And they kind of specialize in different areas. So for example, Amherst, which is actually located at the University of Florida, specializes in, I guess, MRI science and the use of magnets in studying organic tissue and living organisms.
Now let us see that what type of data is collected or created by MagLab. There are the type of data collected varies depending on specific research project, but here are some of the example. The first is the magnetic field data. MagLab researchers measures magnetic field using a variety of techniques, including Hall sensors, magnetometers, and superconducting quantum interference devices, also called as QUIDs. These measurements produce raw data in the form of voltage or current readings, which can be used to calculate the strength, direction, and effect of magnetic field on materials. The second type is the spectroscopic data. MagLab researchers use various spectroscopic techniques such as nuclear magnetic resonance, NMR, and electron paramagnetic resonance, EPR, to study the energy levels and interactions of molecules and materials. This produces raw data in the form of signal intensities and frequencies, which can be used to analyze the chemical properties and structure of materials. Third is imaging data. MagLab researchers use imaging techniques such as magnetic resonance imaging, MRI, and electron microscopy to visualize materials and biological systems at the atomic and molecular level. This produces raw data in the form of images or spectra, which can be used to analyze the structure and function of the molecules and materials. The fourth type that we're going to discuss is the computational data. The researchers use advanced simulations and modeling techniques to study the behavior of materials and biological systems. This produces raw data in the form of numerical values, which can be used to analyze and predict the properties of new materials or to better understand complex systems. Does MagLab have data products generated from the raw data? The answer is yes. There are multiple ways in which MagLab generate data. However, we're going to discuss some of them here. The first one is graphs and charts. The researchers use software tools to plot and visualize data, creating graphs and charts that illustrates the trend and the pattern in the raw data. These graphs and charts make it easier for researchers to understand and interpret the data. The second is database. MagLab maintains database for processed data that can be searched and queried by researchers. These databases may contain metadata, annotations, and other information that make it easier to find and use the data. The third one, and which I find really interesting, and if everybody has like interest in just playing around with alternating current and capacitors, they have great simulations present online. So the third one is models and simulations. The researchers use the raw data to develop models and simulation that can be used to make predictions and test hypotheses. These models and simulations are often more user-friendly than raw data and can provide valuable insight into the behavior of materials and biological systems. The fourth one is the software tools. MagLab researchers also develop software tools that can be used to analyze and process the raw data. These tools may be designed for specific research applications or maybe more general purpose, allowing researchers to manipulate and analyze the data in a variety of ways. Now let us look at some of the instruments that are captured, that are used to capture the data. So as Gareth mentioned, there are 7 user facilities which are spread across 3 main locations within US. And all of these facilities have different kind of instruments, like measuring instruments. Here are some of them are mentioned here: the resistive magnets, superconducting magnets, 100 Tesla magnets, 300 Tesla single turn magnets, solid state spectrometers, MRI scanners, 10 Tesla superconducting magnets. And here there is more into the inside of how these 7 facilities are spread across 3 main campuses. The 3 main campuses that they're spread across is the University of Florida, University of Florida, Florida State University, and Los Alamos National Laboratory. So that is high PT facility, DC field facility, ion cyclotron resonance facility, ICR, electron magnetic resonance facility, EMR, pulsed field facility, nuclear magnetic resonance, NMR, and advanced magnetic resonance imaging and spectroscopy, AMRIS. Now let's understand how is the data being processed. There are multiple complex ways in which the data is being processed. Through some of the researches that I could understand, the published peer-reviewed publications that I could understand, these are some of the common things that I could note in most of the researches. First is the image processing, data visualization, statistical analysis, signal processing, and high-performance computing. The data that has been processed at MagLab is done close to the site of data capture. This is because the large amount of data generated by high field magnets and other instruments used at the user facility require high-speed data transfer and processing capabilities that may not be available remotely.
Okay. So data is collected and archived at MagLab using principles that they go with the FAIR data management plan, which was touched on I think a couple of weeks ago or last week. So the FAIR data management plan is a set of regulations concerning the capturing, sharing, and archiving of data that comes from systems used at facilities. So the MagLab uses that too. So data collected at the MagLab must be archived within the MagLab's computer systems. And if data is archived or saved on like a personal system used by a researcher there, a copy of that data has to be given to MagLab for their storage as well. It can't just be, it can't just belong to the researcher. It has to be shared with MagLab as well. Okay, so according to MagLab's FAIR data management plan, data collected at MagLab is required to be made public either after publication, so after the researcher decides that it's ready to be published, or after a period of 3 years. The MagLab website includes lots of public access to publications of data and research collected at all of their different facilities. This also includes patents and, well, publications of research. So on the hardware side, for data collection, MagLab uses a couple different types, well, many different types of advanced probes inside their magnets. The probes are specialized for different purposes, such as collecting data from living versus non-living subjects. For example, the picture on the lower right, I think, no, I didn't include the picture, but there was a probe that they had which specialized in collecting data from small living organisms, such as like mice or small rodents. And data collected at the MagLab is uploaded into the system, as I said earlier, which for some reason runs Mac operating system.
Okay, so another common question is what are like data movement challenges? And because MagLab is located in a remote rural area of Tallahassee, Florida, the network infrastructure is not as robust as it would be in like more urban areas. And then slow network speeds cause delays in transferring data to remote locations for analysis, which makes it harder to conduct interdisciplinary research with other experts in the field. And then MagLab is located, just as they previously mentioned, 200 miles from the nearest research and educational network connection point in Gainesville, Florida. And just to expand on these important challenges, security concerns and infrastructure limitations are both growing issues because with the increased risk of cyber attacks, data transfer security is a major concern for all research institutions. But as previously mentioned, MagLab's remote location makes it even more vulnerable to security breaches, which could compromise sensitive research data. And then the distance between MagLab and the nearest research and education network connection point, as like I said, in Gainesville, Florida, could create logistical challenges for infrastructure upgrades. And then this could limit the institution's ability to improve its network infrastructure to meet the needs of its researchers. And then
Next slide. There we go. So MagLab was founded in 1990 and since has become one of the leading magnet research facilities in the entire world. And as Gareth mentioned earlier, its headquarters are located at FSU. In addition to this, their pulsed field facility is located in New Mexico and is one of the most powerful magnet labs in the world, capable of producing up to, I think it was 100 Tesla. It was established in 2001 and has since played a crucial role in advancing and research in high energy physics, condensed matter physics, and material science. Their DC field facility is located in Tallahassee, Florida, and is one of the largest and most versatile magnet labs in the whole world. It was established in the early 1990s and it's become a major hub for research in condensed matter physics, material science, and engineering. And their high BT facility, also located in Tallahassee, specializes in producing high magnetic fields in a range of temperatures, and it was established in the early 2000s.
Okay, technically the presentation time is up, but why don't you go ahead and have your final thoughts?
Okay, so really quickly, so recently the institution has made significant updates in cyber infrastructure. They've been prioritizing data storage, organization, and analysis. And one of the key updates to their cyber infrastructure is the MagPick system, which is just a system that allows users to store, organize, and manage data from various sources. And another important component is the HPC cluster system, which provides researchers with powerful computing capabilities for running complex simulations and analysis. And then one last slide. Yeah, there it is. So MagLab's looking to expand its capabilities in the area of clean energy storage, which is becoming increasingly important as we shift toward renewable energy resources. And then this entails developing new technologies for storing and distributing energy, as well as innovating approaches to energy generation. And then I won't go into all the examples just because we're out of time, but another area of focus for MagLab is the conservation of oil supplies through the manufacturing of liquid fuels. And then by developing these more efficient and sustainable methods for producing liquid fuels, the institution hopes to reduce our dependencies on non-renewable resources and mitigate the environmental impacts of energy consumption. And that's all. So thank you all so much for listening. I apologize for going a little over, and if you have any
which we'll be referring to for the rest of this presentation as OOI. So I'll be your first presenter. My name is Margaret Archibald. I'm an oceanography and marine engineering technology student at Maine Maritime Academy. Calloway.
I'm Calloway. I'm currently a sophomore at IU studying computer science.
My name is Mark Onders. I'm a sophomore at the University of Notre Dame, and I'm majoring in applied and computational mathematics and statistics.
And lastly, I'm Areeba. I'm a senior at IUPUI, and I'm also studying computer science. So moving forward, let's first discuss why really this MF matters. What is OOI trying to do, and how is it trying to do it? So OOI, as already said, stands for Ocean Observatories Initiative. So if we go to the next slide, it is an ocean observing network that next slide. There we go. So OOI is an ocean observing network that provides real-time data using more than 900 instruments to address issues that have to do with our oceans. This large-scale oceanographic research program does this by having platforms and sensors located throughout the Atlantic and Pacific Ocean. So for the past 25 plus years, OOI has been accumulating data about ocean conditions and its environments. By doing research for such a long period of time, not only are they able to observe short-term changes, but they can also observe long-term changes. Now, my group members will go into this in a lot more detail, but OOI has 5 arrays that collect all sorts of data, including physical, chemical, geological, and biological. These marine arrays contain 45 different types of 900 instruments, and then these instruments measure more than 200 different parameters. My point is, a lot of data is being collected, and then this data is used for research and education. The data is available to anybody that has an internet connection, but specifically in terms of research, OOI wants the data to tell them what changes are happening in the oceans and how do those changes affect us, our environment, and the ecosystem around us. And so that sums up OOI's mission and how they go about it.
Now for the timeline of OOI. As you can hopefully all see, I have placed a graph on the right of the lifespan of OOI as a whole. The concept of OOI has not even been around for 3 decades, so all in all, it is a fairly new major facility. 2 key takeaways from this graph is that all the way at the beginning, you can see that in 2000, the idea of OOI was approved by the National Science Foundation as a major research, equipment, and facilities construction project. That lasted for 16 years, when in 2016, they became a fully commissioned major facility. Overall, the National Science Foundation has stated that they plan to fund OOI for at least 25 years or longer.
So obviously there is not one person behind this MF. OOI is a consortium, which means that we have a group of organizations that are coming together, they're pooling their resources, their expertise, their efforts to accomplish a goal. In this case, the goal is to operate a network of ocean observing systems and infrastructure. A consortium is often formed by independent entities such as companies, universities, research institutions. In the case of OOI, we have multiple academic and research institutions as well as government agencies. OOI is managed and coordinated by the OOI Project Office at the Woods Hole Oceanographic Institution. We have different organizations such as the Oregon State University and the University of Washington that are responsible for building specific components of the OOI system. And once more, in terms of how this science is being conducted, we have multiple sites that are laid out in the Atlantic and Pacific Oceans. Currently, there are 2 main observatory arrays. The first one is the Coastal Pioneer Array off the coast of New England in the Northwest Atlantic Ocean. And the second one is the Global Argentine Basin Array in the Southwestern Atlantic Ocean. And so that tells us the overall operating structure of this MF.
The data life cycle at OOI.
Yeah, so
Oh, did you want to go?
You don't mind letting me start. So to kind of the heart of the data lifecycle, it branches off in multiple ways, but it all starts with the equipment that collects the ocean data. We have, as previously mentioned, a majority of the research they do, the base is mooring. These mooring arrays, there's currently 5 active mooring arrays, but there are several others distributed that either are in process, are being moved, or have not been connected to the network yet. These mooring arrays, which you can kind of see in the picture a little bit, but it looks like a kind of pancake. It's blue on the bottom, yellow on top. That is a foam floating structure. That's the mooring platform. It houses solar panels to keep electricity flowing to the equipment so they can be installed for upwards of a decade at a time. I mean, the most recent mooring array that's been moved, I think, was installed for about 5 years. So they can theoretically be out there indefinitely, but they have their own power supplies so that they can stay out for as long as the project requires. Those mooring arrays, the floating platform is then connected to the equipment housed at either the seafloor or along the cable with a type of cable that can share data through the wiring. So the wire that connects the floating platform of the mooring to the bottom of the ocean transmits electricity data back and forth and connects the equipment to each other. Each mooring array has its own set of equipment depending on what the operating institution wants to study in that area. So each mooring array can be fitted with a variety of sensors. But you can see different data points online connected to each site, which differ from site to site, which is allows the operating institution to have kind of put their own unique spin on what the array is being used for. But that's also where the different institutions that collaborate on this project come into play, because different developers and whatnot are able to tailor equipment or create equipment for the needs of the research, which is something that OOI, it's really important that they've connected all of these efforts, these scientific efforts in all parts of the science food chain to be able to allow something like this to happen on such a big scale.
For archiving data, OOI archives both unprocessed data and processed data for long time preservation. A lot of OOI's future plans is to include the improve the archival of unprocessed data for like future processing. They store archive data in multiple formats to keep bit rot from affecting any format in particular, such as tape, hard disks, and flash media, as well as cloud backups and other offsite locations. And talking with Jeff at OOI, he said that a lot of their tape storage could be improved because right now it's literally just sitting underneath his desk. So there's no real like online detection method for seeing if there's if the data is still accurate. So it could be useful to look into improving that specific area. For their data distribution, OOI distributes most of their information publicly, and with information that may have like private information, you have to contact to get access, or if it has, anything in particular that would keep it from being publicly accessible. The main way of accessing this data is through OOINet, which is like their legacy data management panel. And they also have the OOI Data Explorer, which is like their new and improved management system. And that provides like a ton of visualization and a lot of like tutorials on how to get started with the data. They also have a blog where they release also some visualizations, and yeah. So their backend stack is almost all of their software is open source, and they either buy it or a lot of it's just produced in-house, and it's all just released on their GitHub organization page.
Now looking at the types of raw data that OOI deals with. On the left, you will see a figure that shows some of the hundreds of processes that operate throughout the ocean. OOI collects physical, chemical, geological, and biological data from the air-sea interface to the seafloor. They state, in specific, they focus on climate variability, ocean food webs, and biogeochemical cycles, coastal ocean dynamics and ecosystems, global and plate scale geodynamics, turbulent mixing and biophysical interactions, fluid rock interactions, and the subseafloor biosphere. They are able to do all of this by having instruments all over the ocean, above and below the water. In specific, all of the data at OOI is real-time data received from the 5 different arrays. In total, this data is coming from over 900 instruments of 45 different types, studying over 200 different parameters of the ocean processes. Data product algorithms are used to make data products, all of which quality assurance tests are applied to and annotations made upon. All of OOI's data is open source and available to the public. For data processing at OOI, the cyber infrastructure backend is made up of the core software components of OOI. These components are responsible for storing, processing, and delivering OOI data and metadata to the end user. Some of these include Apache Cassandra Data Store, PostgreSQL database, Stream Engine, EDEX, and the thematic real-time environmental distributed data services, and the ERDAP file store. Most of this processing is done in the Cassandra database. This means that the shore station is only maintaining level 0 data briefly, and then they send it to the main labs. On the left is a figure showing how data moves in the processing period at OOI. First, we have Cassandra. Cassandra is a free and open source NoSQL database management system. Most of the parsed but not processed OOI data resides after ingestion into the system. Cassandra forms the core of most of the data. Data is then moved from here to other places. PostgreSQL. This is used to bring from index to database. Stream Engine. This processes data and makes data products. EDEX. This is a software framework that serves as an interface to users. Stream Engine and EDEX allow people to calculate data on demand. Threads, temporary storage of data for pickup by end user. And ERDAP. Users can specify data requests, and this returns it in various formats. One example of this is they can request to receive it in MATLAB.
And lastly, to finish this off, in terms of the future work, OOI wants to get the average citizen involved. They want people to actually understand how OOI data has the potential to change the shape of classroom instruction and to advance ocean research. And they're specifically doing that by developing their resources and their programs. For example, they're trying to use Jupyter notebooks so that they can create dynamic tutorials. They want to create a better front end so that the visualizations actually make sense. And lastly, they're also working on documentation to get more people acquainted with how to use OOI data for their own personal research. And so for the future for OOI, besides continuing to research, advance their technologies, advance their network, is all about introducing OOI to the world and beyond. And so those are our resources that we used. And I think that we can conclude it here.
So my name is Mahee. I'm a freshman at the University of Iowa, and I'm majoring in computer science.
Hi everyone, my name is Nardine. I am a senior studying computer science at IPI.
Hey, I'm Bhagya. I'm a first year at UC San Diego, and I'm studying data science.
And the major facility we researched is CHESS.
So CHESS stands for the Cornell High Energy Synchrotron Source, and they mainly focus on high intensity X-ray sources. So they have been supported by multiple foundations, as we will see later in the presentation. But one of the big foundations that supported them was the National Science Foundation. And basically their goal is that they provide users the arts synchrotron radiation for research in physics, chemistry, biology, environmental and material science. They are currently based in Cornell University in New York.
So to help you better understand our major facility, I'm going to briefly give you an overview of how the CHESS particle accelerator works. The accelerator complex creates electron and positron particles and accelerates them to near the speed of light. Electrons are emitted by an electron gun and first accelerated in the LINAC and then transmitted to a circular accelerator or the booster synchrotron, which is similar to the on-ramp of a highway. The positrons travel faster and faster through radio frequency cavities until they reach the speed of light. Once these electrons have reached the desired energy level, they're then injected into a circular storage ring called Caesar, where they circulate in a vacuum environment at a rate of 400,000 times every second. Special magnets called undulators suddenly disrupt the path of the positrons as they travel, and this disruptive process leads to the emission of an intense beam of light. This light in the form of an X-ray is called synchrotron radiation and is directed down a separate beamline while the positrons continue around the ring. Beamlines and experimental stations called hutches make up the research facility of CHESS. In accelerator physics, a beamline refers to the trajectory of the beam of particles, including the overall construction of the path segment along a specific path of an accelerator facility. A variety of optical instruments, such as beam splitters and mirrors, are set up along a beamline to adjust and focus the path of the X-ray in order to create the desired characteristics necessary for each experiment. The X-rays emitted by the electron are directed towards the beamline situated tangentially to the storage ring in the experimental hall. Each beamline is designed for use with a specific technique or for a specific type of research. CHESS X-ray beams are about 100 million times more intense than those produced by X-ray machines in a medical setting and can be used to image materials to the nanometer. Scientists come from all over the world to use this technology.
Okay, so moving to their structure and organization. So CHESS is organized around 3 partner programs, as I mentioned earlier, and they are basically, they are the 3 that fund them. So one of them is the National Science Foundation, which again was mentioned on the very first slide. The second one is the Air Force research, and they are also funded by the National Institution of Health, which is the NIH. Recently, they also proposed a new project or foundation to the National Science Foundation, which will basically focus more on becoming partners and supporting developers with their specific missions. Their science mission is basically to advance the use of high energy X-rays. They recently made an upgrade that involves replacing their old magnetic devices, which was used to call the wigglers, with a smaller and much better magnetic device called udlers. So basically, the wigglers and the udlers were usually outfitted along the beam pipe in the Cornell electron ring. But what makes the new version, which is the udlers, better than the old version, the wigglers, is that they deliver much more energy X-ray intensity, which opens up the field of research to become more advanced for everyone to use. Besides that, the udlers will also be able to focus the X-ray beams on the small spots, which tend to be kind of like a challenge in the past. And they also, when they were compared to the size and the weight of the old version, which again was called the wigglers, they were found to be much smaller and much easier to work with. And they were more efficient because they first produced 20 more times the X-ray that was given to the electron or the beam energy. And they were also proven to be 50 more times efficient with the X-ray experiments that were used to on them than what we currently have. So as far as their data creation and data collecting, CHESS uses, or the CHESS users collect raw data from the X-ray detectors. Most common types of data, as you could see on the screen, are the diffraction imaging, the absorption spectra, and fluorescence spectra and tomographic images. CHESS users also collect metadata about their experience. Some of these are like the experiment conjections, sample description, and many more. The raw data is then analyzed to exact the physical, chemical, and the structure properties of these samples, such as the element composition, the protein structures, and the strain maps.
So as Nardine mentioned before, when X-rays hit a sample, they're either absorbed or scattered, and then these scattered rays are then collected by a state-of-the-art detector and recorded. And then this gives us information of the structure and elemental composition of a sample. The three main types of measurement techniques used are spectroscopy, scattering, and imaging. So data is processed in the experimental hutch. The sample is positioned and a detector system collects the experimental data. There are many types of detector systems, each specialized for a particular application. Two new detectors developed by Cedar Technologies are now available for user experiments at CHESS. They are called the Mixed Mode Pixel Array Detector and the Keck PAD. The main component of an experimental hutch is the diffractometer, including various motorized translations and rotations that you can use to control your experiment. Most macromolecular crystallographers coming to CHESS to collect diffraction data use the oscillation method, which is a time-tested and very well understood technique. Several factors must be considered to collect good data in the most efficient way possible, because each user gets limited synchrotron time. The Flex X beamline can be fully controlled via remote desktop connection for routine data collection. It allows for macromolecular crystallography, standard crystallography, serial crystallography, and high-pressure cryocooling. Data can be processed on-site or remotely, but it is recommended to start processing the data almost immediately after capture or during capture if you're doing crystallography, because radiation damage causes the crystal to die pretty quickly. Frequently, you can catch errors in data collection or machine problems by processing your data during capture. If you wait until the end of data collection, you're stuck with what you have because your crystal has long since died from radiation damage. The collected diffraction data can be indexed, integrated, and scaled using software such as XDS. Additionally, MagChess provides a full suite of software for processing crystallography data. Chess offers remote data access, which I mentioned before. This means scientists and users can send in samples and collect data from the comfort of their homes by simply logging onto their computers. This resource is actually being utilized by a few universities, which offer courses through which students can remotely collect crystallography data from chess without having to fly into the lab. Remote users will miss out on some cues such as PA announcements, audible feedback, and chess control panel indicators. But a webcam viewing app, Hutch TV, is available to assist you in keeping track of the auto monitor state and visually verifying mounts and dismounts. Hutch TV provides views from 4 cameras, including the X-ray count gauges and the physical PHI motor angle setting. Hutch TV also has a delay setting, which can slow down the video rate if you're having bandwidth issues.
Now I'm going to talk a little bit about chess's data archival methods. So the class IT group stores and archives data for long-term storage. So class stands for the Cornell Laboratory for Accelerator-Based Sciences and Education. Our MF chess falls under class. Class broadly is a group that studies the world around us by using X-rays and high-energy electrons. So their IT group maintains a redundant 10 gigabyte high availability Linux cluster to serve and secure centralized storage for chess. Now, historically, chess uses low data volumes with less than 1 gigabyte per user group and different storage solutions for each staff scientist. However, in the past few years, data archival methods have been changing due to a number of factors. One of these factors is time-resolved experiments. An example of a time-resolved experiment is time-resolved spectroscopy. Next slide, please. This is the study of dynamic processes in materials by means of spectroscopic techniques. As we know, spectroscopy itself is the study of color as generalized from visible light to all bands of the electromagnetic spectrum. Now, another reason that the data archival methods have been adapting is because of the NSF data sharing policy, which we've gone over in class as well. Essentially, according to this policy, researchers are expected to share the primary data, samples, physical collections, and other supporting materials that were developed during work that was funded by the NSF. They're supposed to share all these materials with other researchers within a reasonable time frame. All these two factors have led to a shift in chess's data archival methods, including increased centralized data storage and more on-site data analysis. Here on the slide, you can see the chess data flow. Chess DAQ refers to chess's data acquisition system, which is used to collect and process data from various detectors that are used at the facility. Chess Maya is a specialized X-ray detector system that's used for high-resolution imaging. It was named after the Maya star cluster, which is located in the constellation Taurus. Now, the Maya detector is a type of X-ray fluorescence detector. This basically means that it detects X-rays emitted by atoms in a sample that have been excited by high-energy X-rays generated by the synchrotron source. The Maya detector in specific is a key driver of growth in chess's data volumes. It collects an average of 500 gigabyte per user group to run. When we're talking about the chess DAQ and chess Maya, after every run, 2 copies of the data are written to tape. 1 copy is stored off-site. This is the disaster recovery copy. And data at chess is archived indefinitely. I'm just going to go over data dissemination at chess really quick. Essentially, it has 3 main methods of dissemination. One is the public website, which provides information about the facility, as well as articles, presentations, and other documentations. Next is the chess data archive. This gives researchers with access to chess experiments access to raw data, process data, and analytical tools. Last of all is the centralized computing at chess that's based on Linux. In terms of the different software and hardware tools chess has, the very first I'd like to talk about is a software called EPICS that stands for the Experimental Physics and Industrial Control System. Essentially, this is used for control and data acquisition from the various experimental stations at chess. Additionally, the facility has developed a number of in-house software tools, like the Cheetah data processing software. Next slide, please. The image you see on this slide is chess's synchrotron radiation facility. Essentially, the white ring that you see is a 768-meter storage ring. Now, this houses a variety of beamlines and experimental stations for users. The facility itself, other than this storage ring, they have a suite of instrumentation, including detectors, cameras, and other devices that are used to measure and analyze data. As far as chess's future goes, they plan on developing a central software repository. Now, this is great for a number of reasons, but to name a few, this will lead to improved collaboration and a more standardization of software development practice. And it also is really just going to help improve security by providing a more controlled environment for code development and management. That's about all we had planned for today. Thank you so much for your time.